Hello children, welcome to my school exams. Today we are going to discuss the applications of Gauss law. So we all discussed about Gauss law in the previous class. So what is Gauss law? Gauss law states that the number of field lines across any closed surface is equal to 1 by epsilon naught times the net charge enclosed in the surface. That is electric flux pi is equal to Q by epsilon naught. This is Gauss law, right? And we have already discussed about electric flux also, which says that phi is equal to E dot ds, that is equal to E dot s, right? This is electric flux. So now we also know that charge cannot be individual when you are dealing with practical situations. We know the charge distribution is continuous, and we saw three different types of continuous charge distribution: line charge distribution or linear charge density, then surface charge distribution, and finally volume charge distribution. So each of them we had a notation. For line it is lambda, which is equal to Q by L. And for surface, it was sigma, which is equal to Q by area, because area A. And for volume, it is rho, which is equal to Q by V. Okay. So these are the notations that we were discussing for continuous charge distribution. So now with this understanding, we are moving on to the applications of Gauss law. Gauss law is used to calculate the electric field at any point surrounding a charge or a continuous charge distribution. So here we are going to calculate the electric field for three different conditions. One is electric field due to an infinitely long wire. You know what is infinite, right? Infinitely long wire. Second case will be electric field due to a sheet. It is a 12 for a sheet. Okay. Third one, to calculate the electric field due to a spherical shell. So we will be discussing all these one by one. So for these discussions, we will require the recap that we did. That is this one, and this one. That is the continuous charge distribution will be required. Let's see the first one. That is to calculate the electric field due to an infinitely long, straight, uniformly charged wire. So we have already told you, while we discussed about continuous charge distribution, that we are expecting the distribution to be uniform, the same thing. Okay. So for that, you here you can, as it is in the diagram, you can see that we take a wire which is having uniform charge distribution throughout. As it is infinitely long, we do not know the lower end and the upper end, right? So the charge density is denoted by lambda, as we saw earlier. So now we are going to take a point P somewhere near this wire. Okay, let point P be at a distance R from the straight wire. So this distance is taken as R. So you know that the field lines are generated radially outwards, right? So for according to Gauss law, to calculate the electric field at this point, what we should do? The first step is to draw a Gaussian surface that will enclose this charge. So here what I am going to do is, I am going to take a spherical Gaussian surface, cylindrical Gaussian surface with radius R. Okay, the point P will lie on the cylindrical Gaussian surface. This is the first step. Okay. And now if you see here, the field lines will be generated radially outwards. And if you take two charges, so this field line and this field line will cancel. Only the field line that are radiated outwards will be contributing to the electric field. Okay, whatever perpendicular directions will cancel out. If you take the top surface and the bottom surface, we have discussed about area vector in the previous classes. The area vector is perpendicular to the direction of the electric field. So phi is equal to E dot ds cos theta. Cos becomes 90, so that it is 0. So that here in the top and bottom surface, the electric field in the perpendicular in this direction, that is in the direction of the area vector, is 0. That is why we say that electric flux through two flat surfaces is 0. And here the direction of the field and the area vector will be same in the curved surface. For a cylinder, you know, there are three surfaces from your grade 9 and 10 mathematics, two closed top and bottom surface. Third one is the curved surface. So the field lines will be radially outwards only in the curved surface. There is no like field lines in the top and bottom surface. And the reason why the top and bottom surface doesn't have any electric field is given here, because the electric field lines are radially outward and the area vector is perpendicular to electric field. That is what we saw. We drew it diagrammatically here. Okay. With this understanding, now we have to do the mathematical calculation and find out the electric field due to this infinitely long wire at a point P with the cylindrical Gaussian surface. So we know that phi is equal to E dot ds. Also, phi is equal to Q by epsilon naught. So when the left hand side are equal, can we equate the right hand side? Yes, no? So equate the right hand sides. You get E dot ds is equal to Q by epsilon naught. So when this ds is integrated from the bottom to top, minus L to L, you can write it as, this is top part, right? You can write it as E dot S is equal to Q by epsilon naught, right? What is the surface area of this cylinder? It is 2 pi RL, right? 2 pi RH, curved surface area will be 2 pi RH, but we are taking the cylinder as length L. So this is equal to 2 pi RL. So now you can substitute that here. E into 2 pi RL will be equal to Q by epsilon naught. And again, for line charge density, the continuous charge distribution. For line charge, in continuous charge distribution, we saw the notation to be lambda is equal to Q by L, right? Lambda is equal to Q by L. So now Q will be equal to lambda L. Now when you substitute that here, you will get it as lambda L by epsilon naught, right? So this we'll keep it in a box for you to understand. So now you can keep the, we are going to calculate the electric field, no? So keep it here, the electric field separately. Now write Q by, we have to substitute lambda L here, right? So lambda L by, because Q is equal to lambda L, we have seen here. Lambda L by, bring this 2 pi RL to the denominator. Epsilon naught is already present here. Okay, nothing. Substitute Q is equal to lambda L and keep the epsilon naught as it is. Bring the content of what is the surface area to the denominator. L and L will get cancelled, right? So you will get it as lambda by 2 pi R epsilon naught. And this electric field is a vector quantity. So put a direction vector n cap to indicate that it has a particular direction. So for all vector quantities, indicating the direction is mandatory. If you have not practiced in that way, please have a understanding of vectors and learn to indicate the directions, because directions are part of the quantity that you are describing, you cannot ignore them. Okay. So now the typed format of what we discussed now is given here. Pause the video. Please take notes of this. Then we will continue with the next application. Now we'll go to the electric field due to a uniformly charged infinite plane sheet. So as you can see in the diagram, we have taken a sheet. Okay, so there is charge distribution. We are taking a small surface del S. We are going to calculate the charge here and the electric field due to the surface, then integrate it for the entire sheet. As the charge distribution is uniform, you can integrate it when you calculate it for a small area. Okay. So here in this figure, if you see, this is a cylindrical Gaussian surface that is taken. Gaussian surface is an imaginary surface. I hope you remember the previous class information. Again, in the textbook, there will be a cuboidal Gaussian surface. You will get the same result as you get when you take a spherical surface. Okay, so I have opted for spherical surface. If you want, you can draw a cuboidal surface also, as it is in the textbook. So now you can, in the cylindrical surface, you can see that the field lines are radially outward, right? So this direction and this direction, there will be field lines, and the area vector and the electric field are parallel to each other in these two. Whereas if you see here in the curved surface, the area vector and the electric field are perpendicular to each other. So there is no flux lines. Here in the perpendicular direction, the fluxes, field lines are 0. So that it doesn't contribute. Only this surface, surface 1 and surface 2 will contribute to the electric field at this point P. The point P, I hope you have seen here. It is here. Okay. So now the explanation for that. So as it is a sheet, we'll go for surface charge density. So consider an infinite plane sheet of charge with uniform charge density sigma, the notation for surface charge density. So now we are imagining a Gaussian cylindrical cylinder of cross-sectional area A, normal to the plane of the sheet. So electric field lines are parallel to the curved surface. Flux through the surface is 0. That is through the perpendicular surface, this surface. Okay, curved surface is 0. Okay. So now with this, we are going to calculate the electric field at this point P by using the same method as we discussed previously. Here instead of line charge, we will be using surface charge distribution. So phi is equal to E dot ds. Again, phi is equal to Q by epsilon naught. Okay. So now as earlier, we will equate the right hand side because LHS are equal. Now this E dot ds. You have electric field here. You have electric field here, right? So it will be equal to E dot ds will be equal to EA plus EA. What is this A? Area of the surface. Okay. Electric field will be uniform because the charge distribution is uniform. So electric field into area. Okay, 2 times. So it is 2 into EA. And due to continuous charge distribution, you know that sigma is equal to Q by A. So from this, Q will be equal to sigma A. Correct? Now substitute 1. This is, we take this 1, take this 2, and this 3. Substitute 1 and 2 in 3. So what will you get? E dot ds, you will substitute as 2EA. And instead of Q, you will substitute as sigma A by epsilon naught. So AA will get cancelled and you will get E as sigma by 2 epsilon naught. So from this, and again electric field is a vector quantity, put a vector notation. N cap. So from this you understand that the electric field is independent of the Gaussian surface or the area of the Gaussian surface that you take into account. So that is the reason any Gaussian surface you take, you will get the same answer. Okay. So electric field is sigma by 2 epsilon naught n cap. This is the typed version of what we discussed earlier. Please pause the video, take notes, and then continue for the next application. Now coming to the third one, electric field due to a uniformly charged thin spherical shell. You all know a shell, right? Shell means it is hollow inside. It is a shell, okay? So here also we will account for surface charge density. So we are taking a spherical shell of radius r with uniform surface charge density sigma. So now we are going to take a point P. So that this diagram we will see first. So this is a uniformly charged spherical shell with radius r. Okay. So now we are going to take a point P somewhere here. And we have a Gaussian surface. Okay. So the field lines are directed radially outwards. So the radius of this Gaussian surface is taken as small r. Okay. So by similarly, how we did previously, we are going to apply the same method and we are going to calculate the electric field. Pi is equal to E dot ds. Pi is equal to Q by epsilon naught and sigma is equal to Q by A. Q by A, right? Q upon A. So Q will be equal to sigma A. So now, like you have to substitute all these things. First of all, equate this two, right? So E dot ds is equal to Q by epsilon naught. So now, what will be the value of ds or s here? What is the surface area of a sphere? So here in this E dot ds, we are going to calculate the electric field, right? So that will refer to the Gaussian surface area of the Gaussian surface. So that will be 4 pi small r square because small r is the radius of the Gaussian surface. So E into 4 pi small r square will be equal to Q by epsilon naught. Q is equal to sigma A. Sigma. And again, area will be the area of the spherical shell. So that is 4 pi r square. See, the charge is enclosed in the spherical shell, right? So we are taking the area of the spherical shell here divided by epsilon naught. We have substituted ds and q in this formula. Okay. So now keep E separately. Sigma by epsilon naught, keep it 4 pi r square by 4 pi small r square. No, small r square. 4 pi cancel. So sigma r square by epsilon naught r square. This is the electric field due to a spherical shell at a point P outside the shell. Now what if this point P is on the shell? Somewhere here. At a point P on the shell, R will be equal to R, right? So that means this equation will reduce to sigma by epsilon naught because this R and R, when it becomes equal, they will get cancelled. Okay. And inside the spherical shell, there is no charge. So there is no flux lines there. Field may exist, but flux will not exist. Flux lines are lines that are perpendicular to the surface where you are calculating. Here there is no flux. So that the electric field inside this spherical shell is 0. Exactly. Okay. So this is the typed version of what we discussed. Please pause the video and take notes. So now you can see the field inside the shell. Gaussian surface is again, we are taking a Gaussian surface here inside. Okay. The formula for flux is written and charge enclosed by this Gaussian surface is 0. So what happens? Q is equal to 0, so E will be equal to 0. The electric field inside a charged spherical shell is 0, as we discussed earlier. Now this is the diagrammatic representation. Inside the shell, E is equal to 0. On the surface of the shell, E is equal to sigma by epsilon naught. And at a point B outside the surface of the spherical shell, E is equal to sigma r square by epsilon naught r square. R is the radius of the shell and small r is the radius of the Gaussian surface. Now, this is the graphical representation. If you can see, the electric field is 0 from the origin till the surface of the spherical shell. From there on, the field becomes maximum and it starts decreasing with regard to 1 by r square. So, it falls off with regard to 1 by r square. So, these graphs are important for MCQ questions. I hope this applications of Gauss law concept is very clear to you. If you have any doubts, please raise your questions in the comment section. We will be happy to help you. Thank you.